All right. What we did, we looked at the feedback before, last time, and we saw that the feedback has an interesting property. So we saw that if you have a large gain, what the feedback does is that basically creates a transfer function, a closed loop transfer function that was determined mostly by the feedback. Then the next thing we did, we also looked at the effect of what happens if you have some dynamics, some frequency dependence in the forward path and the feedback path. And one of the things that we saw is that if you had dynamics in the forward path, in the gain A, that effect was kind of suppressed as long as your gain to AF, gain times the feedback ratio, that product was large enough. And then also we looked at the effect of some dynamics in the feedback path, and what we saw there is that actually that dynamics, that transfer function got inverted in the terms that basically if it was a rational function, its poles became the 0 and the zeros became the poles due to the action of the feedback if you had a lot of gain. So now, today we are going to look at the effect of feedback on nonlinearity, or the effect of nonlinearity in the feedback loop. So we'll talk about two different cases. So this was our general model for the feedback. You had an amplifier with a UI plus and a UI minus, and then you had a feedback network. Now let's assume at this point, let's assume that this is scalar. You have an input x, and then you have an output y. Now, what we will do that will be a little bit different now is that we introduce this nonlinearity in the forward path. So this nonlinearity, for example, can be a transfer function like g of x, whatever. Could have some shape. For now, let's say it's like for now, assume it's some sort of a memoryless nonlinearity. That's like a one-to-one transfer function from some inputs to some output, right? Now, let's assume that we have this, and we want to see what the feedback loop does in the presence of something like this. So let's find out. Let's write the equations. What we're interested in is like the relationship between x and y. So what do we know? We know that this is x, obviously ui plus, and then ui minus is what? Is y times f. So we know these two. F is still linear scalar. So we know that this output is going to be a times x minus fy. This minus that times a. Right? And then the nonlinear function is applied to this, whatever this value is, to produce y. So this is a relationship. This is a general relationship for any kind of nonlinearity G. So what we are trying to solve, essentially, what we're trying to find is we are trying to solve for y in terms of x in general, which, as you can see, is hard. But there's something that's a little bit easier, which is solving for x in terms of y. So let's try to do that. So if we apply the inverse function g minus 1 to both sides, what we'll get g minus 1 of y, right, equals a times x minus fy. And then now it's easy to solve for x. So you can see that x is basically fy plus g minus 1 of y, g inverse of y, divided by a. Okay? So this is the relationship that you can find out. You can say, well, I can't find y in terms of x, but I can find x in terms of y in the general form. Now, what does this tell us? Well, okay, whatever, right? You can see it's some general function. But what if feedback is really operating the way we want it to? Ideally, how would this feedback loop operate? If you were looking at it kind of like where the ideal thing is, or if you want kind of an asymptotic transfer function or something like that. I mean, it's nonlinear, so technically you can't say it's an asymptotic transfer function. But what happens if A becomes very large? So what happens if A goes to infinity?
Which just looks like our linear feedback relation.
Right, because this term will disappear, right? Because you have an A in the denominator. So this term becomes incredibly small. So what you have is that x equals fy, which now you can solve to know that your y over x is basically 1 over f, which is the h infinity determined purely by the feedback path. So what did it do? What did this large gain do? So in principle, these two can be combined into one thing. They could be one thing. It could be a very nonlinear amplifier, like the ones that we've made before, right? I mean, they were highly nonlinear amplifiers, have exponentials and things of that sort in them. But what it tells you is that if you have even a highly nonlinear amplifier that has a lot of gain, then essentially its nonlinearity will disappear in the feedback loop. And you will get a gain that's both linear or linearized and determined purely by the amount of feedback you apply. So feedback, one of the major things it does, it actually reduces the distortion, the nonlinearity in the system, right? By this action. And you can see it's very general. I mean, the way we wrote it is for any general nonlinear function. As long as your gain is large, you can basically suppress the amount of nonlinearity that you will get. And this was the main reason, by the way, actually, that in the negative feedback was first used. And Harold Black, who has a patent, has filed a patent on this, was working at Bell Labs, and it was actually sitting on a ferry. The problem was that they had these relays, multiple stages of relays for transcontinental and transatlantic phone lines. And the nonlinearity of different stages added up so that there was too much nonlinearity in aggregate. So what they said, what he thought is that, okay, if I apply the negative feedback, I can actually make it more linear, make the circuit more linear by applying this feedback and make these amplifiers trade gain with linearity. Because, see, here's the thing. Reversing, I mean, both of them can be done, but if you lose, let's say, some of your gain, you can always recover it by adding more of these stages. If you have a nonlinear distortion, it's harder to recover it because then you have to kind of introduce the inverse function, and it has to be matching, and it has to be always matching, and if the parameters of the circuit changes, as the temperature changes, the designs from one device to another device changes, matching it is harder. But this way, you guarantee linearity, and you add more gain stages in cascade. So that was the fundamental trade-off. So you see that it basically kills the effect of nonlinearity in the forward path. So now, for example, let's look at an example. So let's say you have a cubic nonlinearity, or basically a nonlinearity that's written, so this g, so g of x is the cubic root of x, or x to the power of 1/3. It's a better notation, really. But, so that's what that is, right? So this kind of nonlinearity, how does it look like? So it basically kind of looks like some sort of a saturating nonlinear, something like that. I mean, it's not exactly saturating, it keeps going, but it's compressing. It's a compressing nonlinearity. We call it compressing, but if you just basically put a sine wave, the tips of the sine waves are just going to be compressed. They're going to be squished, right? So if you put a sine wave into it, it would kind of like squish the tips of the sine wave, the peaks. So let's say you have something like this. Of course, if you plug it into this thing, you can easily see that you go here, you see x equals f of y plus y cubed over a, right? If you just basically applied it. I mean, we are just doing the inverse of that. We're using this equation, and you would get something, right? So that to see how it works, let's try we've tried 3 examples. So let's say that you have a stage, that this nonlinearity, with 3 levels of gain. So the first one is with a gain of, the plot on the left is done with a gain of 100, 10 to the power of 2. So if at the gain of 10 to the power of 2, you will see that they basically, the closed loop and the open loop transfer function are kind of like, in terms of nonlinearity, are about the same. I mean, you have reduced the nonlinearity a little bit. The green curve is the one that basically you get after the closing of the loop. Now, if you look at the middle curve, that's with a gain of 10 to the power of 4, in A of 10,000. Now you will see that it looks more linear. And if you go to, for example, the last one, the one on the right, that's with the 10 to the power of 6. With that gain, you can see the nonlinearity is almost linearized completely, as expected. Right? So that's kind of like it shouldn't be that surprising to you. So that's one example. Another example, which we can do, is basically by looking at we can look at actually a transistor level one. Let's do a transistor level one. So I'm going to erase this because we've seen this already. It's not that sophisticated. I'm just going to open up a little bit of room here. So let's say this circuit we've seen before. So we had this feedback circuit with a bipolar amplifier, let's say, R2, oh, I'm sorry, R3, R2, R1, and R2. And then you have a V in and a V out. Right? We looked at it from an H infinity perspective. We looked at it from the asymptotic transfer function perspective before. We'll look back at this again from different perspectives. But OK, so now let's look at it from a treat it as a nonlinear device. So let's look at the nonlinear state. Now, you can write the exact equations for this. And you can try to solve them. You have to solve them numerically when you see it because it becomes an exponential equation also. So we make some simplifying assumptions to get some sort of an analytical result. And then we'll compare it with what the simulation tells us. That does take the nonlinearity fully into account and see how well or how poorly they compare. So what do we know? When you have a lot of feedback, if you have sufficient amount of gain. So first of all, we know this is an exponential dependence, right? So an exponential, and it's highly nonlinear. This behavior of this transistor. So the assumption we make is that beta is much greater than 1. So we don't have to worry about the base current. So that's one assumption we make because we don't want to worry about it. If we don't have to worry about the base current, from a large signal perspective, right, what is this? So we know that this current is essentially the same as that current. Right? They have to be the same. This current going in has to be the same if base current is very small or if it's 0. So then V in minus, so let's call this capital V in and capital V out, because we're talking really about nonlinear large signal stuff now. V in minus, now what is the voltage here? The voltage here is VBE of the transistor. Right? So that is the voltage drop across this resistor. Divided by this resistor is the current through that resistor. And we equate it to the current through this resistor, which is going to be VBE minus V out divided by R2. Right? Now, I can solve for VBE, so I can multiply it out, and then what you will get is that basically you will get R2 V in minus VBE equals R1 VBE minus V out, and then you move this term to the other side, you get R1 plus R2 VBE equals, move this here, so this becomes R2 V in plus R1 V out. Therefore, VBE, which includes two parts, which has the quiescent DC VBE, or VBE on, whatever the DC voltage is, plus the fluctuations over that, right, is equal, well, approximately, because we're making this assumption really here, is R2 V in minus R1, plus R1 V out over R1 plus R2 from this equation. Okay? We just solve for VBE. I didn't do anything magical, basic algebra. So what do we get now? Well, one thing we realize is that actually, if this is really, the feedback is this is an exponential dependence, right? The dependence on this VBE is an exponential. So it's going to be very strong. So if the feedback is operating properly, these variations should be very small, right? That's the asymptotic equality principle really applied. So in that case, we just assume that this is VBE on. If the feedback is sufficiently strong, so this is VBE on. And if you do that, then what you can do, you can actually, so if you assume this is VBE on, then multiply it out, and you can solve for V out in terms of V in. So you get V out is negative R2 over R1 V in, so I'm solving for V out, plus VBE on times this guy divided by R1. So it's basically 1 plus R2 over R1, approximately. So this is an approximation we've made, and we'll see how good or how bad it is. But what do you see in this approximation? What's the key thing to take? What's the key takeaway? The key takeaway is that even though the device is nonlinear, as long as that exponential is strong and you have sufficient gain, you see a linear relationship between V in and V out, according to this approximation, with some offset. Right? So we can actually pick an example. So we can pick a numerical example here, right? And the numerical example we have here involves these parameters. So for example, if you look at it, you can say, well, let's say VCC is 5 volts. Let's say beta is 100. IS, let's say 10 to the minus 15 amps, and so on and so forth. So you have the parameters. The key parameters are R1, 1 kilo ohm. So these are the ones that we had before. When we tried this example last time, we used these same parameters, 5 kilo ohm and R3 of 1 kilo ohm. Now, if you take these and plot them, calculate this quantity, the VBE on plus 1 plus times 1 plus R2 over R1. So it's going to be, let's say, 0.7 volts times 1 plus 5. So it's 6 times 7, so it's 4.2 volts. So this equation, our approximation, predicts an offset of 4.2 volts and a linear dependence. Okay? Now, let's look at the simulation results. So what you have here, you can see that the transfer function without R2, when R2 is infinity, and with R2. And when you compare them, you see that the transfer function with R2 is highly linear. And furthermore, its offset, if you look at the offset where it crosses the y-axis, is approximately at 4.2 volts, or 4.1 volt in this case, right? Which is what we predicted. So what you see in that plot is very similar to what you expected in the simulation results. So that shows that this analysis actually makes sense from that perspective. So that's one thing to keep in mind. Any questions about that? Okay. Now, this was the effect of feedback in the forward path. Now, what if we have nonlinearity in the feedback path instead? So now let's say our F, the actual feedback network itself, so you have A, ui plus and ui minus, this is x, this is y. Now let's assume that the f itself is a nonlinear function. So what would happen now and why? So what would happen? Well, let's write the equation and see what we can tell. So we know if this is y, this is going to be f of y, right? So what you have is that you have x minus f of y times a is y, right? Because that's x minus f of y is this difference times a produces that output. Now, you can solve again for x in terms of y. So you divide this by that. You say y over a plus f of y. Right? That's what you get. X is y over a plus f of y. But now again, let's see what happens if gain goes to infinity. The gain is very large. You can make it a ka and make k infinity if that bothered you. But anyway, so that's fine. Right? So if a goes to infinity, what happens again this time? So in that case, so let's just say f is going to infinity. Sorry, a is going to infinity. So then obviously this first term disappears, right? So what you will end up with is x equals f of y. But we're interested in the relationship of y and a. X. So y becomes f inverse of x. So again, what we put in the feedback path got inverted. So the transfer function of the overall system, if gain is sufficiently large, right? A is sufficiently large, is the inverse of this function. You've inverted this function. You created the inverse function. Now this is a nonlinearity. We saw that if you put actually some linear transfer function with some dynamics, the dynamics got inverted. You got the inverse function. But now you got the inverse nonlinearity. Why? Why does feedback do this? And you will see there are other functions that if you put in the feedback path will get inverted too. But why is it doing this in principle? I mean, why does this happen? It really goes back to asymptotic equality if you think about it. We said that if you have negative feedback, to have a finite output, this difference should be infinitesimal, which basically means that the feedback works to force this whatever voltage or current or whatever this signal, the value of the signal here, to be equal to that. So when the feedback forces the output of the feedback network to be equal to the input, then the input of the feedback network has to be the inverse of this function, right? So for this to become x, right, the input here, y, has to be f inverse of x, which happens the input to the feedback network is the output of the circuit. So that's why it inverts anything you put in there if you have sufficiently large gain. If it's a nonlinear function, it inverts the nonlinearity. If it's a linear function, transfer function gets inverted. If you have a PLL and you have a frequency divider here, it becomes a frequency multiplier. Because if the frequency here is like 1 megahertz and then your division ratio is, let's say, 8, then this has to be 8 megahertz. So when it gets divided, it produces 1 megahertz. Right? So it's not, I mean, when you think about it this way, it's not that magical. I mean, it's what it should do, but it's the action of the feedback. It forces it to go to the place where this happens. And you did one example of this thing in your problem set, for example, right? I mean, so just like I'm going to do a simple version of that. So let's say you have a feedback network, you have an op amp, right? And a MOSFET. Let's say an NMOS that's like this. So you have a V in, this is R1, this MOSFET is, let's say, square law dependence, and this is V out, and this is gain. So if gain is sufficiently large, then these two have to be equal, which basically means that this voltage has to be 0, this current would be 0, because this voltage is forced to be 0. Now, this current has to be equal to this current, or this current. So basically we say V in divided by R1 has to be equal to negative K V out minus Vt, the threshold of the transistor squared. Let's say it's a square law device. So if you put a square law device in the feedback path, what do you get? You divide it by negative K, so you get negative V in over R1K. You take a square root, and then you add a Vt, so that's V out. So your V out will look like this, right? V out versus V in. Why? Because your MOSFET had a characteristic that looked like this. Right? Does it make sense?
You want the square root of a negative there? Shouldn't it be?
So it means that it's valid for negative values of Vn.
Yeah, I was going to say for your plot it might be easier.
Oh, yeah, actually you're right. No, so sorry, this is incorrect. Thank you. It's actually this way because of that minus sign. Thank you. Yeah, my plot was incorrect. Okay, yeah, so that's what you get. And you can imagine if you put a PFET on the bottom part of it, it would do this, the opposite part. Okay, so that's what the effect of nonlinearity is and a couple of examples in the feedback loop. Any questions on that? Okay.